Hey there. In this video, we're going to be talking about independent versus dependent events, and we're also going to be talking about the multiplication rule. And these are tied together. The way we use the multiplication rule depends on us understanding if an event is independent from another event. So let's take a look. Sometimes events depend on one another. You can do something in such a way that it influences the way something else will occur. For instance, if I draw a card out of a deck, I have influenced what cards could then be drawn later out of that deck. So the second draw is dependent on the first draw. So we have this issue sometimes. Let's look at this example where we toss a fair coin repeatedly. Here are the outcomes. I toss it the first time, I get tails. Then I toss it again, and I get heads. Third toss, heads. Fourth toss, heads. Fifth toss, heads. Sixth toss, heads. Seventh toss, heads. What is the likelihood now of getting heads on the next toss? Now, a lot of people will say, unlikely. I mean, we've had so many heads in a row. Chances are, the more of heads we get, the more likely I'm thinking, man, we got to get tails, right? In fact, it is a fair coin, right? It is a fair coin, so it's got to start acting fair at some point, right? Well, it turns out that no matter how many times you toss this coin, the probability of getting heads on the next toss is always 50-50 if it's a fair coin. Right? The fact that you got a whole bunch of heads in a row has no influence on what the next toss is going to be. The next toss will always have a 50-50 chance of being heads or tails. And that is to say that these events are independent. Your gut might tell you something else. It might say, hey, I'm bound to get tails here next, but your gut is wrong. Every subsequent event is 50-50. These are independent events. So two processes are said to be independent if knowing the outcome of one provides no useful information about the outcome of the other one, and that's the case here. And examples of independent processes. So this is one, tossing a coin repeatedly. Each toss is independent from the rest. Roll a die. Could have done the same example by rolling a die. Each roll is independent from the rest. The die has no knowledge of what it had previously shown, so every roll is independent then from the previous rolls. Draw a marble from a bag, then return the marble, shake the bag. Every draw, if you do this, every draw that you'll get, it will be independent from the rest because you've returned the marble, shake the bag, it's got exactly the same random state that it had the first time. Drawing a card, then return the card and reshuffle the deck. Each draw will be independent from the rest. As long as you return the card and reshuffle the deck between each draw will be independent. Now, there are dependent processes. If you draw a card from a deck and then draw a second card without replacing the first, that would be an example of dependent events. The second draw depends on what happened on the first draw. For instance, if I drew an ace on my first draw, it makes it less likely for me to draw an ace on the second draw because there are one fewer aces in the deck. If I draw a marble from a bag and then just draw a second marble without replacing the first marble, well, these are dependent events. The characteristics of the first marble will influence the likelihood of getting certain characteristics on the next marble because I have removed a type of marble from the bag. If I choose a person from a small group and then choose a second different person, these are going to be dependent events because I have removed one of the people from the group, so the second person I draw, if I removed a male the first time, I'm less likely to get a male the second time because there's one fewer male in the group. So if however, we had a very large group, if the numbers we're dealing with are very large, then typically a single outcome will have a negligible effect on other outcomes. So we can safely treat the processes as if they were independent. All right, so if you had a large group, like in these examples, draw a marble from a bag containing thousands of marbles, then draw a second marble without replacing the first. Well, yeah, technically these are dependent events, but the difference is negligible. Removing that first marble is made such a little difference that practically speaking, the two events are independent. And the second example here, choose a person from a very large group, not a small group, but a very large group, and then choose a second person. Yeah, technically speaking, these are dependent events, but the difference in probabilities is so small that you can treat them as if they're independent. So when the groups we're dealing with are very, very, very large, you can treat events as independent even if they technically are not. And that brings us to the multiplication rule. The multiplication rule deals with ands. So the addition rule dealt with or. The multiplication rule tells us how to deal with and. So the probability of A and B is the probability of A times the probability of B given A. So what is this B given A business? Well, that means it's the probability of B given that we have knowledge about something else having occurred, right? So what we were just talking about in this independent versus dependent events is that if two events are independent, then the probability of B doesn't depend on A, right? So the probability of B given A is the same as the probability of B. So for independent events, this can be ignored, okay? So we can just multiply the two probabilities. So in these first few examples, we're going to look at this case where the events are independent. All right, so examples where it's independent. So for example, toss a fair coin 2 times. Find the probabilities. Right? Heads, 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 tails, tails, heads, tails, tails. Well, the probability of heads, heads, each time you toss the coin, it's independent of the previous toss, so we can just multiply these probabilities together. I can ignore this given part. All right, so that probability of getting heads is a half, and the probability of getting heads is a half, and a half times a half is equal to a quarter. Okay, well, what about the probability of heads, tails? Well, that's the probability of heads times the probability of tails, because these events are independent, and that's again a half times a half. That's a quarter. What's the probability of tails, heads? Well, that's the probability of tails times the probability of heads, and that's, again, a half times a half. That's a quarter. And again, tails, tails. All of these are just independent events multiplied together. They each have probability 1/2, and so they're all giving us 1/4. Okay, let's look at the next one. The next one says, toss a fair coin 3 times, find the probabilities of these 3 outcomes. Well, again, each time you toss the coin, it's independent from the other ones. So when I compute these probabilities, heads, 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 I just multiply them together. So it's the probability of heads times the probability of heads times the probability of heads, or the probability of heads cubed, right? Which is 1/2 each time. A half times a half times a half is 1/8. And the probability of heads, tails, heads is the probability of heads times the probability of tails times the probability of heads, which again is a half times a half times a half. It's 1/8. And you guessed it, I'll let you compute this one out on your own if you want. It's the probability of tails times the probability of tails times the probability of tails. Half times a half times a half, and that'll be, again, 1/8. And finally, roll a fair 6-sided die twice. Find these probabilities. A 1 and then a 3. Okay, so these are independent events. So the probability of 1 and then a 3 is going to be the probability of 1 times the probability of 3, which is 1/6 times 1/6. That's 1/36. What about an even and then a 6? Probability of even and then a 6 is going to be the probability of even times the probability of 6. These are independent events. And the probability of getting an even number, well, there's 3 even numbers, 2, 4, and 6, that you could get on a die out of 6 possibilities. And the probability of getting a 6 is 1 out of 6. So this is 3 out of 36, or it simplifies to 1 out of 12. And then finally, the probability of getting 2 odd numbers, right? So that'll be the probability of getting odd and odd. Well, that's the probability of getting odd times the probability of getting odd. What's the probability of getting an odd number? Well, there are 3 odd numbers between 1 and 6. There's 1, 3, and 5. So that's 3 out of 6. This is 3 out of 6. And so the product is 9 out of 36. Or in other words, 1 out of 4. Okay, that's for independent events. So independent events is very nice because you can just ignore that given bit because it doesn't matter what happened to A. It doesn't influence B. They're independent. All right, so now let's look at some examples where we have dependent events. Okay, so when we have dependent events, this given part will become important, right? So draw a card from a poker deck and then draw a second card without replacement. That means we did not replace the first card. If we don't replace the first card, the outcome of the second card can be influenced by the outcome of the first card. So let's see how this works. All right, so the first part says to find the probability of drawing a spade, and then in the second draw, drawing a diamond. All right, so I'm going to denote spade with an S because it's hard to draw this, and a diamond with a D. All right, so we're looking for the probability of a spade and then a diamond, right? Well, that's the probability of a spade, I'm just using this rule here, times the probability of a diamond given that, and this is often the notation that we use for given that, just a vertical bar, that I drew a spade. Okay? Well, the probability of a spade is there's 13 spades in the deck, and there are 52 total cards in the deck. So the probability of getting a spade is 13 out of 52. Now, what's the probability of drawing a diamond given that I drew a spade? Well, there are 13 diamonds in the deck, so 13. Now, here's the kicker. There are no longer 52 cards in the deck, right? I drew a card, right? So now there's only 51 cards in the deck. So it's 13 out of 51. And if I compute this as a decimal, I get approximately 0.0637 as my answer. Okay, let's go to the next one. Probability of getting a 2 and then drawing a 3. All right, so probability of getting a 2 and then getting a 3 is the probability of drawing a 2 times the probability of getting a 3 given that I drew a 2, because I got a 2 and a 3. All right, so what's the probability of getting a 2? Well, there are 4 2s in the deck. Okay, so it's 4 out of 52. And what's the probability of getting a 3 given that I drew a 2? Well, there are 4 3s in the deck, but there's 1 fewer card in the deck. There's only 51 cards left. So it's 4 out of 51. And that is, as a decimal, 0.0060, approximately. Okay, let's look at the part C here. A diamond and then a red, right? So probability of a diamond, I'll use D, and then I get a red, I'll use R. Okay, so that's the probability of getting a diamond times the probability of getting a red, given that I drew a diamond. Okay, well, diamonds. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 diamonds in the deck, right? So 13 out of 52 is my probability. Now, what's the probability of getting a red given that I drew a diamond? Well, how many reds are in the deck given that my first draw was a diamond? Well, there's 13 in this row and 13 in this row. There's 26. Or are there? Wait a minute. I just drew a diamond. See, given that I drew a diamond, that means one of these diamonds is missing from the deck. There are no longer 13 of these, there are only 12 of these left. So there's 12 of these, and there's 13 hearts, that's 25. There are 25 red cards remaining, not 26. And there's 51 cards in the deck because I've drawn a card. So it has updated both the numerator and the denominator here. And when I compute this, I get approximately 0.1225. And finally, the probability of getting two hearts, right? So heart and a heart. So I'll just use H and then another H. Okay, well, that's the probability of getting H times the probability of getting an H, given that I already drew an H. Okay, well, what's the probability of drawing a heart? Well, there are 13 hearts in the deck, so that is 13 out of 52. Now, what's the probability of getting another heart, given that I already got a I pointed at the wrong thing. Getting a heart, given that I already got a heart, right? Well, how many hearts are left? Well, I already drew a heart, so there's no longer 13 hearts in the deck. Now there's only 12. Right? So there's only 12 hearts remaining. And how many cards are there in the deck? Well, I drew a card of the deck, so there's no longer 52. There's 51. And when I compute this, I get 0.0588, approximately. So you can see how the dependent events are a little bit, you got to think a little bit harder about these and think about how the first event influenced the second event. Let's look at another example where we have dependent events. Here we have a bag consisting of 1 red, 2 yellow, 3 green, and 4 blue marbles. Okay, that means there are a total of 10 marbles in the bag. Draw 2 marbles without replacement. That means after you draw the first marble, you don't put it back in. You draw a second marble without replacing the first, right? So that means the first draw will influence the second draw. Okay, so let's compute these. All right, so in part A here, I want the probability of getting a red and then a green, right? So that's going to be the probability of getting a red times the probability of getting a green, given that I drew a red. Okay, let's think about what these are. What's the probability of drawing a red? Well, there's only 1 red marble in the bag, and we said there's a total of 10 marbles, so that's 1 out of 10. What's the probability of getting a green, given that I drew a red? Well, there are 3 green marbles in the bag, and how many marbles are left in the bag total? Well, there's only 9, because I drew a marble from the bag, so now there's only 9. So the probability would be 3 out of 90. Or if you wanted to simplify that, 1 out of 30. Okay, what about having both marbles drawn be green? Well, that means you drew a green, and then you want to know the probability of getting a green given that you got a green, right? That's what the rule says. Okay, well, what's the probability of drawing a green? Well, there's 3 green marbles in the bag, and there's 10 marbles. So 3 over 10. What about the probability of drawing a green given that you drew a green? Well, now how many green marbles are in the bag? You drew a green, so there's only 2 left. How many marbles are left? Well, we drew a marble, so instead of 10 marbles left, there's only 9. So that is 6 out of 90. So that is simplifies to 1 out of 15. And the third one here, neither marbles are blue. Okay, well, that means that we got not blue, so blue complement, times the probability of getting blue complement given that you got blue complement, right? So this means not, right? So what's the probability of getting not a blue? Okay, well, there's 2 ways to do this. You could take the probability of getting blue and subtract it from 1, right? Or we could just count up how many are blue. Let's just do it that way. So there are 6 marbles that aren't blue, so it's 6 out of 10. Now, what's the probability of getting another marble that's not blue? Well, we just drew a marble that wasn't blue, so there's no longer 6 of those left. There's only 5 of those left, right? Because we just drew one of those. And how many marbles are left? There's only 9. So here we have 30 out of 90, or in other words, 1 out of 3. So the probability of dependent events.